Hello, this is Dr. Moses taking you through this course of Survey in Organic Chemistry. Chapter 1 will cover bonding and making of isomers. We call that isomerism. Of course, you're looking at structures which look like organic structures, but before we go to complex structures like this, we'll have to break it down and show how bonds are made. Okay? Show how bonds are made and show how different arrangements of these bonds will give you the isomers of structures which have the same formula. Okay, let's dive in. So, all these chemicals are made from the smallest particle. We call it an atom. The atom is the smallest particle of an element. Elements belong in periodic tables that retains all of the chemical properties of that element. So the smallest particle of an element that carries the respective chemical properties of that element is called an atom. You can't break it further down. It's the smallest. And in fact, to justify that point, look at the mass. It's 1.66 times 10 to the negative 24. Like, it's very, very small. Okay? And the diameter is given to be 1 exponent negative 10 to 5 exponent negative 10. Okay? Or 100 to 500 picometers, very small, or 1 to 5 angstroms. These are just conversion factors. That's meter, this is picometer, that's angstrom, where an angstrom is equivalent to 10 to the power negative 10 of a meter. You know, the meter that we use to measure distance. Yeah. So the atom is very small. Inside the atom, you have subatomic particles. We call them subatomic particles. So the subatomic particles in the structure of an atom include protons, neutrons, and electrons. So this will be denoted as P, N, and E. Sometimes we give it E minus. Sometimes this is given as P plus. It's a proton. Okay, neutrons are neutral. Protons will be positively charged. Electrons are negatively charged. The protons and neutrons are found in the nucleus of the atom. So inside the nucleus of the atom, which is always in the middle, you get protons and neutrons. Just like when you break an egg, you get the yolk. So the nucleus will be the kind of the yolk of the egg. And then electrons will be found outside the nucleus in electron clouds that we call shells. Okay? So electrons will be dancing out. If I would ask you, what's the charge of the nucleus? If the neutrons are neutral and the protons are positive, then the nucleus should be positive. And the electrons are negatively charged. Opposite charges attract. That's why these electrons are kind of attracted towards the nucleus. One would consider the sun and the planets, which would be the electrons. So you have that kind of pull, magnetic pull towards the nucleus. We call it effective nuclear charge, ZFF, that pulls electrons towards the nucleus. Okay, so the protons and electrons are charged. Obviously, protons are positive. Like I said, electrons are negative. The neutrons are neutral, as the name goes. The charge is almost gonna be given as 1.602 to the power negative 19 coulombs. I think that's the charge of an electron. And in terms of coulombs, but just know again, the electrons will have a charge of minus, protons will have a charge of plus. Okay, generally negative and positive. Neutrons have no charge. Okay, so in the modern days, the atomic structure will have the mass of an electron being 5.468 at 10 to the minus 4 atomic mass unit. We call it AMU's atomic mass unit. The proton will have 1.07, and then the neutron will have 1.087. Out of these, you still see that the electron is the smallest. The charge of an electron is negative, proton is positive, the neutron is neutral, 0. These two are found in the nucleus. The protons and the neutrons are found in the nucleus. Electrons are always outside in the shells. Okay, so the protons and neutrons are almost 1800 times the mass of an electron. Electrons are very small. Here is a representation of the volume occupied by electrons, shaded yellow. The nucleus is right in the middle, and then obviously there's a comparison of the distance in between, but just know this cloud, these electrons, even though it seems that they're occupying a larger diameter, they are spread all out, just like the clouds are spread in the sky. Remember again, electrons are smaller than protons and neutrons. Okay, so the clouded area, the yellow shaded area, has much volume than the nucleus, because the electrons will randomly repel each other and create a larger size of the atom. So the volume will be increased. Most of the volume of an atom is due to the electrons, and of course the electrons are negatively charged. Like charges repel, so you get a greater volume outside because the electrons want to occupy the maximum possible space available. Okay. Most of the mass of the atom is due to the nucleus. Again, because protons and neutrons are heavier than electrons. So if you want to find the mass number of an element, you'll have to sum up the number of protons and number of neutrons. If you want to find the atomic number of an element, you have to, in fact, of a neutral species, which is an element, then you'll have to consider the number of protons, which have to be equal to the number of electrons for the atom to be neutral. If they are not equal, then you either have a positively charged species, we call it a cation, or a negatively charged species, we call an anion. Alright, so isotopes. Isotopes have the same chemical properties. The only difference is their masses and how they decay in nuclear decay processes. So what causes them to have different masses? Okay, we will have to crack that down. Now look at boron. Boron has two common isotopes, B10 and B11. Both have 5 protons and 5 electrons, but 5 and 6 neutrons respectively. Going back to the definition, so isotopes will have different masses. The reason being, they have same number of protons but different numbers of neutrons. Okay, now going back to boron, if I may ask you, how many protons and neutrons are in boron? If you look at the periodic table, boron is gonna be in, I think it's the 3rd column of the periodic table, is gonna have the atomic number of 5. Okay, which means it should have 5 protons. And in fact, it has 5 protons and 5 neutrons. That's why the mass of boron will be 10. Because remember, I told you the mass number is equal to number of protons plus number of neutrons. Here, number of protons are the same, so it's still a 5, which means the number of neutrons is 6. And that's what this statement is saying. So they are isotopes because they have the same number of protons but different number of neutrons. And they might have different half-lives or decaying rate in nuclear decay processes. Now, in reactions, in chemical reactions, if you did not learn it in general chemistry, chemical reactions happen by involving electrons. So you're either going to be losing electrons or you're going to be gaining electrons, or there's going to be a sharing. So this is how you make bonds. Either electrons are lost, gained, or shared. Okay, so valence shell electrons are the outermost shell of electrons and are involved in chemical bonding. Again, those electrons in the outermost shells might gain more electrons or might lose electrons. The valence shell, the outermost shell in the structure of an atom. Remember, I told you have a nucleus and then you have shells, right? So electrons residing on the outermost shell, we usually denote electrons with dots. That's how we can represent them, and they're usually paired unless they're not enough to pair. So the outermost electrons, the valence shell electrons, are the ones which are used in bonding. One bond is made by 2 electrons. So you use 2 electrons to make a bond. So for example, if you have hydrogen, you have a bond in between it. This simply means that you have hydrogen with 2 electrons in between it. These 2 electrons must be valent electrons. Remember, hydrogen is in group 1, so it has 1 electron, 1 proton. So each of these hydrogens will donate those electrons. We use fish hook arrows to bring single electrons, double arrows to bring 2 electrons. So that's how you make this bond, and that's how you make hydrogen gas. Again, it's the valent electrons that are used to make bonds. They are the highest energy, S and P electrons. Those are the ones used to make bonds. Now the shortcut you can use is, if you can identify the main group count or the number of the main group on the periodic table, then that will automatically give you the number of valent electrons in the valent shells. And it's useful only to show the outermost electrons, which may be used in bonding or not bonding to give you lone pairs. So we use Lewis symbols for that purpose. Now if you look here, let me skip all the way. If you look here, all these elements, okay, so the columns are called groups, the rows are called periods. So all these elements in group 1, main group 1 I should say, have 1 valent electron. For example, hydrogen will have 1 valent electron. That's why you only see 1 valent electron. Lithium will also have 1, sodium will have 1, potassium will have 1, rubidium will have 1, cesium will have 1, francesium will have 1. Now, the shortcut I'm trying to tell you is, if you can count the main group element, if you can count the number, if you can determine the number of the main group, then you can quickly tell the number of valence electrons. I am going to disregard the transition metal elements. Usually we don't use those for organic chemistry or inorganic chemistry, but anyway, for general chemistry review part in chapter 1, I'm not going to talk much about it. So I'm saying main group elements because those are the ones I'm only considering. That's main group 1, main group 2. Skip all this mess. Those will be in the general number of groups. So come here and call this main group 3, 4, 5, 6, 7, and 8. So all these elements will have 1 valent electron. All these will have valency of 2. All these will have valency of 3, 4, 5, 6, and of course the last group will have valency of 8, with the exception of helium, which will have a valency of the outermost electrons will be 2. Obviously helium does not have 8 electrons. So you see, it only has 2 electrons, but the rest will have 8. The reason why helium is placed on main group 8 is because it has fully filled 1s orbital. We'll talk about that shortly. So that's the shortcut on how to quickly tell the valency of the number of valence electrons which may be used in bonding in elements of the periodic table. Now let's go back. Okay, so we use dots to represent electrons. By now you've realized that, like, hydrogen will have 1 valent electron, helium will have 2 valent electrons, chlorine will have 7 valent electrons because it's in the main group 7. Let's talk about how electrons are arranged in atoms. This is called electronic configuration, and you're going to be tested on this. Electronic configuration, configure is to arrange. So configuration, electronic configuration. How are electrons arranged? So electrons arranged in orbitals, you have the s orbital, the p, and the d. The s will take a maximum of 2 electrons, takes maximum of 2 electrons. The p will take a maximum of 6 electrons, and then the d will take a maximum of 10 electrons. Okay, so the first shell, which is usually the closest to the nucleus, will always be filled by a maximum of 2 electrons. Okay, this one will only carry 2 electrons. If you go to the second shell, number 2, it's gonna take a maximum of 8, and then the next one will take a maximum of 18. Yeah, so and so forth and so forth. But you don't need to memorize that. I would want you to write electronic configurations using the SPD. Remember, the S takes a maximum of 2 electrons, the P takes a maximum of 6, the D takes a maximum of 10 electrons. So let's use a pyramid, this pyramid, to write electronic configurations of some elements. So if I were you getting into the test, I'll quickly draft this pyramid and then use it to answer the questions. And it's very simple because the first row, the first column is the S's, the second one is the P's, the third one is the D's, which takes a maximum of 10, and the fourth one is the F, which takes a maximum of 14 electrons. I told you the D takes a maximum of 10 electrons. Next, I'll explain shortly. And then you have the G. We rarely get to the G. In fact, for the purposes of this class, I won't get to F. The maximum, the farthest will go is the D. Now, consider the places where the electrons are leaving to be boxes. We call those orbitals. So S will take a maximum of 2. And then the P, since P takes a maximum of 6 electrons, then you're gonna need 3 of those boxes, or 3 suborbitals for the P orbital. And then the D will take 10, so you'll need 5 of these suborbitals, where the electrons denoted by the arrows that I'm drawing will occupy maximally 2 of them per box, per orbital, and they should be of opposite spin. You must have learned that in general organic chemistry. So this is a representation of Fs, that's a representation of P, this is a representation of D. And then of course, if you want to go with F, you'll have to draw 7 of those boxes, but we'll not go that far. So now let's write the electronic configuration of hydrogen. So hydrogen has atomic number 1 in the periodic table. Let me show you the periodic table. It's a periodic table. So usually the smaller number in the box will be the atomic number, the bigger number will be the mass number. Obviously the mass number is not shown here. because I don't need it in my class that much. So helium has atomic number 2. So okay, let's go back. Hydrogen has atomic number 1. So the electronic configuration will be 1s. Helium has atomic number 2. Okay, this is 1s1. Helium has atomic number 2, so it will be 1s2. Lithium has atomic number 3, so it will be 1s2. The s orbital is filled because it takes a maximum of 2 electrons. Then we have to go to, so when 1s is filled up, we go to 2s. So we go with 2s and give it the extra 1 because we have to account for the 3 electrons in the atomic number. So the electronic configuration of helium is 1s2, 2s1. Beryllium has atomic number 4. So the electronic configuration will be 1s2 filled up. Then we move to 2s, 2s2, the second shell. After the first shell is filled up, we go to the second shell, 2s2. And that takes care of the 4. Boron has atomic number 5 in your periodic table. Boron is right here. It has atomic number 5. Okay, so in that case, boron will be 1s2, 2s2. Now we still have one more. So we've covered the 1s and 2s. So we go at the back of the arrow, we have to cover the 2p before 3s. So we write 2p, 2p1. So you see there's 2p1, there's 2s2, and there's 1s2. Sorry, it should be for boron. So that's how you do it. Now let's do for carbon. Carbon has atomic number 6. Following the pyramid, you have to cross the 1s, 2. S takes a maximum of 2 electrons. 2s2, and then 2p2, because now we have to account for the 6 electrons. 2 plus 2 plus 2 is 6. That will be the electronic configuration of carbon. Let's take a crazy one like argon. Argon has atomic number 18, so it will be 1s2, 2s2. We go to 2p before 3s. P can take a maximum of 6. We can give it 6 because we have more than enough electrons to arrange. After the 2p, we go to 3s, so 3s2. Now we have 12, and then 3p6. So cover the 2p before the 3s, cover the 3p before the 4s. This will be the electronic configuration of argon. Alright. Now one for magnesium. The magnesium has atomic number of 12. So again, I'll go 1s2, 2s2, 2p6. I've used 10, and then 3s2. Now, there is another term called noble gas. Noble gas electronic configuration. Otherwise called abbreviated electronic configuration. I'm just gonna leave it in shorthand. So you know, noble gases have fully filled orbitals. So like if I were to consider carbon, if this was the complete the normal electronic configuration, so if I am to write the noble gas electronic configuration of the same, I'll look for the fully filled orbitals. Obviously it's the 1s and 2s. 2p is not filled because p usually takes a max of 6. So I would bracket the ones that are filled up, and then anything that's left stays outside. Okay, so Actually, you can see that the one, actually, let's see, that's not it. Did a mistake there. So I'll bracket this 1s2, not the 2s2, because this shell is not filled up. Remember we said that the second shell should take a maximum of 8. Obviously 2 is here and 2 is here. If you sum up those electrons, they are 4, they are not 8 on the second shell. So only the first shell is filled up. So the abbreviated will be, see, look at the element that's right above carbon in the noble gas column, and that will be the shorthand for 1s2. In this case, it's going to be helium, because helium happens to have 2 electrons in the noble gas, and then the rest will be written outside. So these are usually called core electrons, and these ones are called valence shell electrons that we talked about that are used to make a bond. So carbon will have 4 valence shells, 4 valent electrons, and you'll see 4 dots because the second shell is not fully filled. Remember we said that the second shell must be filled up by 8 electrons. In this case, the second shell only has 4. Okay, let me give you the shortcut again. So if you want to write the noble gas electronic configuration, which is helium in brackets 2s2 2p2 for carbon, one would just go to the periodic table and spot where carbon is. Carbon is right here. So upstairs, the immediate noble gas we have is helium. So one can use helium, which accounts for 2 electrons, and then you move one step, second step, third step, fourth step. You see, that's a count of 4, which accounts for these 4 valent electrons, and that also puts carbon on the main group 4 of the periodic table based on the valency. Okay, let's do the same for magnesium. I'm gonna choose a different color. So for magnesium, I see that my 1s is filled up, my 2s is filled up because it takes a maximum of 8. 3, the third shell is not filled up. It should take a max of 18 according to our table here. So our core electrons will be the 1s2, 2s2, 2p6. 10 electrons, 10 core electrons, and then the valent electrons will only be 2. So to write the noble gas electronic configuration, I'll use the 10 electrons in the periodic table in the noble gas. If you go to the noble gas, you'll see that neon has atomic number 10. And in fact, your shortcut, magnesium is down here on the 3rd period. Go to the 2nd period. Up there, you see neon. So that's the noble gas element that needs to be bracketed. That takes care of the 10 electrons in the 12. And then you're left with 2, which happens to be the 3s2. So magnesium has 2 valence electrons. It uses those 2 electrons to react. In fact, it loses them to be stable, because chemicals react only to gain octet state stability. We'll talk about that shortly. So this will be the noble gas electronic configuration, while this one is called the complete, where you don't shorthand it. It's called the complete electronic configuration. Your book might not state it that way, but that's what it is. Okay, so you practice with the rest and see if you can generate the electronic configuration going up the scale using the pyramid. So remember, we just said that carbon has 1s2, 2s2, 2p2, and we determined that only this 1s2 will be the core, and it's taken with the helium. So you have 2s2, 2p2, the second shell is not filled up, So you have 4 electrons unaccounted for, not used in the abbreviation in the bracket. So those are the 4 valence electrons, and that's why carbon is in the 4th main group, right? So this comes from there. Do the same thing with bromine. You're gonna be left with the 4th shell unfilled. That will be the valence electrons. Just write the noble gas electronic configuration. You're gonna get all these things. Aluminium has atomic number of 13. Let's do that and see. So the complete electronic configuration is 1s2, 2s2, 2p, 6, 3s, 3s2, 3p1. Obviously my 1s and 2, the first shell and the second shell are filled up. First shell filled up by 2 by rule, second shell filled up by 8 by rule. The third should be filled up by 18. We don't have enough, we only have 3. So this will give us the core electrons, which will still happen to be neon, because that's what's right above the aluminum. Aluminum is on the 3rd period, neon is on the 2nd period in the last 8th main group elements. So the noble gas electronic configuration generated from the complete will be neon in brackets 3s2, 3p1. This part right here is what you have here. So you have 3 valent electrons, which are these 3 dots. Do the same for cesium. So this snippet here is just showing you the main group elements from main group 1 to main group 8, assuming and disregarding the transition metal elements, which will be somewhere here. And you're shown the dots, which are just valent electrons, not the atomic number of electrons. Those are just valent electrons, like explained up here. Elements in the same group must have the same number of valence shells electrons in their configuration. They must have the same valence shell electrons. Like group 1s, all of them have 1 valent electron. Groups, what's this, 6 will have 6 of them, like oxygen and sulfur. Group 7, like fluorine and chlorine, will have 7. And then with the exception of helium, group 8 will have 8 valence electrons. Helium has only 2. It's put on the main group 8 because the first shell is filled up. It does not need to gain or lose. Okay, so I've talked about this periodic table, so I'm gonna skip the slide. So if you want to draw the structures of compounds, we use rules called Lewis rules. Lewis octet rules of drawing structures. So it's the scientists that developed the format, the sequence, the process of drawing the structure, the general structure of compounds, showing bonds and non-bonding electrons. So we focus on the octet rule, which is just the rule that counts the number of electrons available surrounding an element to be 8. That's the rule that's going to be used to determine if you drew the best Lewis structure. Atoms tend to lose or gain or share electrons to achieve the noble gas electron configuration. In fact, if you go back here, you'll see that if carbon has to be stable, has to be octet, like to have an octet state, 8 electrons on the second shell, it needs to gain 4 more or lose 4. Because when these elements react, they want to have fully filled orbitals. Either they lose the few valence electrons or gain the few extra electrons to be fully filled and as stable as the noble gases. So that's the octet rule. Some of the elements in the periodic table don't follow Lewis method of drawing structures, but those ones will not be discussed in this class. So there are 2 possible types of bonds to consider. There is covalent, like colleague, where there is sharing of electrons, There's ionic, where there's complete transfer of electrons. So here you have complete electron transfer, but here you have sharing of electrons. So in sharing electrons, either one element is giving the two electrons to make a bond, or each of the partnering elements are donating one electron each to make two electrons which make a bond. Okay, ionic bonding. This is chapter 1, section 2. An ionic bond is an electrostatic attraction between positive and negative ions resulting from complete, I need this to say complete, resulting from complete electron transfer. So like here, what you're seeing, there's an arrow showing that this single electron is going to be donated to bromine. Why? The bromine has a valency of 7, its main group element 7, and its outermost shell lacks 1 electron. So why would we not give it the 1 if sodium is having that extra 1? Sodium is in group 1, so the valence is 1. Bromine is in group 7, so the valence is 7. So this one, if it has to be comfortable, it needs to gain 7 more electrons. If this one, okay, it's either sodium is either gonna gain 7 or lose the 1. These are the two options sodium has. For bromine, it's either gonna gain the 1 to be octet, or it's gonna lose the 7 to be octet, or to be stable, so to speak. So out of the options shown, which one is the best for each of these? Now, it's easier to lose the 1 electron than gain the 7, so sodium will decide to lose. Here, it's easier for bromine to gain 1 than to lose 7, so this is out, this is what will happen. So sodium is like, hey, I have an extra electron, get it. So bromine will take it. This is a fish hook, because it looks like a fish hook arrow. We usually use such half arrows to move 1 electron. Whenever we use double-ended arrows, we are moving 2 electrons. So if you're using a double-ended arrow, this is 2 electron movement, and you need to know this. You're gonna heavily use it in this class. If you're moving 1 electron, then you use a fish hook. So once the sodium loses the 1 electron, then it is 1 negative charge less. So it becomes positive 1. We don't write positive 1, we just write positive. When bromine gains 1 extra negative charge, which is an electron, then it's going to be negative. So the species that are positively charged are called cations. So like this one is a sodium cation. Species that are negatively charged are called anions. So this is a bromine anion, not onion anion. Okay, anions are formed by gaining electrons, cations are formed by losing electrons. The resulting electron configuration of both ions are those of the nearest noble gas, because remember, for sodium, let's see, before sodium has atomic number of 11, so you have 1s2, 2s2, 2p6, 1s2, 2p6, and then you have 3s1. So obviously the 1s, the first shell and second shell are filled up, so that's 10. 10 happens to be the atomic number of neon, and then you have 3s1. This single electron that's lost is gonna be this single electron here. So once it's lost, subtract 1 electron, you're gonna be left with neon. That is stable, because now all are filled up, all shells are filled up. The bromine has atomic number of, let's see, what's the atomic number of bromine? Where is my periodic table? Bromine has atomic number of 35. So let's try and build for bromine down here. So the neutral bromine has atomic number of 35. So we should go 1s2, 2s2, 2p6, 3s2, what's our pyramid again? So 3s2, 3p6, 4s before 3d. Okay. 4s before 3d. But let's see, I have 10 to this point, I have 10 to this point. So the 3d can get 10, and then I can write 4p, 10, 20, 30, 40, 4p, 4p5. Okay. So the question is, who is your outermost shell? Our outermost shell is number 4. So you have to look all over the place and find the outermost shell is number 4, which means this will give me my valence electrons because it's the valent shell, the outermost shell. So bromine has a valency of 7. Valency of 7 because the fourth shell has 2 and 5. That's where this 7 comes from. So the rest of the orbitals are called the core electrons, which is 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d10. These are core electrons. And then, of course, now the 4s2 and the 4p5 will be outermost because they are in the outermost shell, which gives you a valency of 7 electrons. So bromine will rather gain one more electron, which is one more count to get 8. Okay, of course, this p here is a p5. If you want to fill up the p5, what do? You know, p takes a maximum of 6 electrons. So this is empty. It needs one more, and sodium is giving it. So now, if you were to write the electronic configuration of this, now at the end on the valence shells, it's gonna be the same thing, but out here it's gonna be 4s2, 4p6. So everything is gonna be filled up. And in fact, if you look closely, the noble gas configuration will in this time be krypton, because now the 35 turns out to be 36. So the noble gas electronic configuration after addition, let's see, 1 minute is 10. After addition, you get that the bromine, which was 35, gaining 1 electron, you get 36. That tends to be krypton. So the electronic configuration of the bromine with a negative charge will be krypton. Okay, and that's how this was found. Now for sodium, it has atomic number of 11. Once it loses, so sodium to Na plus. So this has 11. You're losing 1 electron. You're getting 10 electrons. That happens to be the same as the one for neon, and that's how this came by. So the resulting electron configuration of both ions are those of nearest noble gas, which is neon and krypton, respectively. And both of them satisfy the octet rule, meaning all orbitals are filled up after the loss and the gain. Okay, now note that sodium is on the left of the periodic table. That's what PT means, and therefore it has low ionization energy, IE, which means it easily loses the electron. It doesn't take much energy to lose the electron. Chlorine is on the right side of the periodic table, PT. It has high high electron affinity, which means it really wants to grab an extra electron. So in fact, there's a term called electronegativity, which is the affinity of an element for electrons. Like the element really wants to gain electrons. So whenever you go across the periodic table, sodium is somewhere here, chlorine is somewhere here on the periodic table. So chlorine is farthest to the right, so chlorine is more electronegative. It really needs the electrons, just like bromine did here. Bromine really needed the electrons, so bromine is farthest to the right of the periodic table. It has high electron affinity. It's gonna readily grab it, and sodium will readily lose it because sodium does not have as much electron affinity. So then it's generous. It wants to give it away. It doesn't want to get hold of the single electrons. It wants to release it. It's generous. It wants to give it away. Low electron affinity for sodium, high electron affinity for chlorine and bromine. That's why sodium transfers an electron to chlorine, bromine, iodide, fluorine, etc. Ionic bonding is common in metals and nonmetals. For example, K and Br. Metals are usually found group 3 going backwards, and metals are usually found between group 3 and 7. So like, let me show you. So main group 1, 2 up to main group 3, those are usually metals. But you have exceptions where the yellow line crosses, those are called metalloids. The ones shaded in orange in this periodic table in your book, those are the nonmetals. And of course, you have the key here. You can tell which ones are nonmetals, which ones are metals. Let's see. Yeah, see, this is a nonmetal. The ones that are orange are nonmetals. And group 7, main group 7, those are halogens. They are also nonmetals, but specifically they are called halogens. Then of course main group 8 are noble gases. So ionic bonding is characterized whenever you have a metal, and you see this much in your book in chapter 1, and a nonmetal. For covalent bonding, it's between two nonmetals. So KBr, KCl, NaCl, ClCl2, you know, I would KOH, such things are ionic. NaOH, sodium hydroxide, those are ionic. But something like H2O, both of these. Hydrogen, even though hydrogen is put on the side where you have metals, hydrogen is usually classified as a nonmetal because of much of its chemical properties. So hydrogen and oxygen are nonmetals, so that's obviously covalent bonds between the elements to make water. Natural gas called methane, we'll talk about this in organic chemistry. Carbon and hydrogens, again, those are nonmetals. I've told you hydrogen is not a metal even though it's in group 1. So this will give you covalent bonds, but these structures down here are all ionic. KBr, KCl, calcium chloride, potassium hydroxide, sodium hydroxide. Anywhere you see a metal, a true metal and a nonmetal, expect ionic bond between the metal and the immediate nonmetal bonded to it. Ionic compounds are usually found in crystals, or they usually form crystals. So we call the pattern, the array of the pattern, a lattice or crystal structure, and it's usually a pattern, a clear pattern, organized pattern, not random, of positive and negative species close together. For example, consider sodium chloride, the table salt. this will be taken to be Na, and this will be taken to be the Cl minus, Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus, Cl minus, Na plus, Cl minus, Cl minus, Na plus, Cl minus, Na plus, Cl minus, Cl minus, and so forth and so forth. So you make a pattern that makes a crystal. That's why you see the table salts to be crystals. It's very strong force of attraction because you have opposite full formal charge of opposite charges, plus and negative. Remember, opposite charges attract. Okay, and that's why they are crystalline and very, very, very solid. Okay, covalent bonding. Covalent bonding, like I said, is usually found between nonmetals. So ionic is between a metal and nonmetal. Covalent is between a nonmetal and a nonmetal. I've shown you on the periodic table how to tell which are nonmetals, which are metals. So here they're sharing. In ionic bonding, there was electron transfer. Okay, so where atoms obtain octet by sharing electrons between them, you will be forming a covalent bond. And remember, valent because you're using valence electrons, co because there are two things together, working together. Okay, hydrogen is the simplest example of a covalent molecule, where each hydrogen has atomic number 1, electron configurations 1s1. The outermost valence electron is 1, so I'm using the dots. So when these two guys are joined together, you get hydrogen gas. So the simplest example, neither atom will lose or gain an electron because of course they are of the same type. None of them has a high electron affinity, and also it's also because the ionization energy is too high and the electron affinity is too low. Thus they just have to share. Okay, the bond is a balance between the electrons and the nuclear repulsion and electron nuclear attraction. So what this is saying is, instead of there being one hydrogen pulling electrons than the other, you just have normalized forces of attraction and repulsion. So the two elements are very comfortable between each other, so such that they just decide to share. When you have equal power, none of you will win. The best way for you to have a win-win situation is to share. So forces of attraction and repulsions are almost equal, as shown in this representation here. Okay, now, like I said, one hydrogen will bring its valent electron, the other one will bring, I'm using fish hook because we are moving one electron versus using double-ended arrow where we'll be moving two electrons. So these electrons are not just hanging around in space, they are in orbitals. So whenever these orbitals overlap, or whenever the shells, for example, overlap, there's going to be a common mutual ground here where there's an overlap, and that's where the bond is formed. So that's the bond where we show it with a straight line. Now each hydrogen has the S, the outermost shell filled up, because remember they had one but now they're sharing. So if you consider the one to the left, these two electrons, if you consider the one to the right, these two electrons, so each of them is happy, and that's why they gain the noble gas electron configuration, that of helium, same as that of helium. The bond is commonly displayed as a line rather than a pair of dots. So we would want to show it this way, not this way. Remember, each bond is 2 electrons. Okay, now you realize that here you have equal donation of electrons to be shared. Like You have $1, your friends have $1, you bring the $2 together, you buy something, you share it out evenly to eat. But here it's showing you one species giving the 2 electrons to make the bond. This type of covalent bonding is called coordinate covalent bonding. It's a general version of covalent bonding where both electrons come from one atom. The other partner does not give anything. So ammonia usually has a lone pair. This is ammonia. It has a lone pair on nitrogen. So actually this is an acid-base reaction. We'll talk about this later. So you use your lone pair to attack the positive center, which is H+. Here you have so many electrons. Here this guy needs electrons, evidenced by the plus charge, which means please add some electrons on me. So this lone pair on nitrogen will be donated. This time you're using a double-ended arrow to the hydrogen, and now you make a new bond. So these 2 electrons right here are those 2 electrons in there. Now you end up with what we call ammonium ion, which is just this. Okay, so you made a covalent bond because these 2 electrons, even though they were donated by one atom, they are shared between the 2 partners. There is a difference in what is meant by bond length in ionic and covalent compounds. Ionic bonds, in an ionic bond length, you simply take the sum of the ionic radii of the 2 ions. So for example, if you have sodium plus, probably let's say it's this size, and then you have chloride, which let's say it's that size. So the difference from the center to the center is gonna be the ionic radii. So you just sum up the distances, get the ionic radii. But for covalency, that's not true, because there's an overlap. Where there's an overlap and merging of orbital, then it tends to be, it's true that covalent bonds are shorter than the sum of the atomic radii of the 2 atoms, because there's an overlap. For example, here, see there's an overlap, then the distance will be shorter versus if you were to consider them separate. You know, in ionic bonding there's no overlapping of shells or orbitals. One will go from here to here, from atom ion 1 to ion 2, but in covalent bonding there's overlap, so the distance is reduced. So we simply don't do that, okay, because that will make the covalent bonds to be shorter than the sum of the atomic radii, and that's a key feature in covalent bonds. In summary, ionic bonds are formed whenever you have strong electrostatic attraction between opposite charged ions like Na+, for example, and Br-, or K+ and Cl-. Covalent bonds are made by sharing. The bonds are held together by electrostatic attraction, yes, but majorly they involve two nuclei to the 2 electrons, which spend most of their time between the 2 nuclei. So what this is saying is that the covalent bonds are made by sharing. Actually, the 2 electrons that are making the bond are shared, just to make the statement simple. So if this is element A, you have element B, they're sharing. Now, depending on which of these has high electron affinity, these electrons might dwell closer to B or closer to A, not like right in the middle. For example, if A is more electronegative and you have sharing, these electrons will be somewhere here. If B is more electronegative, which means it has high affinity of electrons than A, those electrons will be closest to B. And that's what causes what we call dipole moments, which will be discussed later. The dipole moments causes partial charges, not full charges, not full formal charges. See here you have full formal charges like +1, -1. In this case you will have partial positive on A, partial negative on B, because B has high electron affinity, the electrons are close to it, electrons are negatively charged. In this situation right here, illustration here, A will be partially negative, B will be partially positive, because electrons are very close to A. Here neither. For example, in hydrogen, where the elements are evenly sharing the electrons, so none of them will have partial negative, partial positive. Okay, so that's what this statement is saying. Covalent bonds are also held together by electrostatic attraction. That's why I have the charges, partial charges, that involve the two nuclei to the two electrons, which spend most of their time between the two nuclei. So it depends which one has high affinity, either towards A or towards B, depending on which one likes to have those electrons close by them. Okay, other examples of Lewis structures of covalent compounds. Chlorine has a valency of 7. So if two chlorides are coming together, you see these electrons not paired, they'll want to be paired, and that's how you make a bond, the sharing. Okay, so that's how you get this bond right there. Okay, I'm going to erase that arrow. Here, hydrogen shares its valent electron with chlorine. These are the two electrons in the bond, you get HCl. So these are covalent products. Unshared electrons are also shown, and they're shown as dots, and we call those lone pairs, because I usually joke saying that they are lonely, they are not bonded to anything, or they are otherwise called non-bonding electrons because they are not used to make bonds. For example, these are lone pairs, these are lone pairs, those are lone pairs. Okay, why do these guys share? Hydrogen is 1s1. Chlorine, let's see, chlorine has atomic number of 17. Let's see, 1s2, 2s2, 2p6, 3s2, 3p5. So I see these are my core electrons, which will give me a neon. Then I'm gonna have 3s2, 3p5. The p is not fully filled, it needs to be 6 to be fully filled. That's why it needs one extra electron, and that's why hydrogen will share it. At the same time, hydrogen needs one extra electron to be 1s2 for the s to be fully filled. Okay, so now that you understand, hydrogen needs to be fully filled to be 1s2, chlorine needs to be fully filled for the P to be P6. So that's why these guys will decide to help each other. They need a symbiotic relationship. So by sharing, hydrogen will now have 2 electrons, because this will be hydrogen right here. And in fact, in this case, I will draw these shared electrons very close to chlorine, because chlorine is farthest to the right and it has a high affinity for electrons. So considering hydrogen that it has 2 electrons, considering chlorine is gonna have 8 electrons. Okay, so every electrons are paired and they are 8, so it's octet rule satisfied. So these 2 electrons shared here are those 2 electrons making the bond. Okay, so I think I've made sense out of it. Shared electrons make a bond, each bond 2 electrons. Same story here, you have 2 hydrogens combining with 1 oxygen. So in fact I'll get rid of that and just bring it here. So I'll show how we are sharing. Oxygen is main group 6, so it needs 2 more electrons to be 8, which is octet. So each of these 2 hydrogens will donate the 2 electrons as shown, and now you get covalency to make water. For ammonia, you will need 3 hydrogens. So one hydrogen will pair up with that single electron, another hydrogen will pair up with this single electron, and another one will pair up with this single electron, and that's how you make these 3 covalent bonds. You realize that this is not used. It's not used. That's a lone pair. Carbon will do the same thing. Each of these hydrogen will combine. Okay, you need one there, you need one here, you need one here to make methane. Of course, carbon has a valence of 4, that's why we are showing only 4 dots. Oxygen has a valence of 6, we are showing 6 dots. Oxygen is in the main group 6. Okay, so in this case, there's a process to be followed to get the best structure where all of them will be octet, and that's gonna be discussed later in drawing Lewis structures. Okay, so now if you were to consider bond length, the triple bond will be the shortest, the single bond will be the longest, and I'll show you an example. Look at CC, CC, CC. Single bond, double bond, triple bond. The triple bond is going to be the shortest, 121. The single bond is 154, double bond is 134. Now for the rest that are shown here, it just depends on what's bonded on it, and there's an argument of size and other things. Now, the more electron pairs that atoms share, the closer the atoms are glued together. That goes with the multiple bonds. A triple bond is shorter than a double bond, which is shorter than a single bond. That's all you need to know in this slide. Don't worry about memorizing the numbers. Okay, we'll discuss polarity and electronegativity later.